Okay. It's fine. Hello, Z. Welcome. Welcome, welcome. Oh, thanks for asking. I feel fine. I already had COVID at one point. So I mean, I'm no scientist, but I think my first shot was kind of like my second shot. So today I feel much better than I thought I would. But yesterday, I don't mean to bum anybody out, but the reason I was not hosting class was because Loaf, my cat, is old. She had kidney problems, and yesterday was her day to move on. So I kind of had to take the day for that. But today we're doing good. Feeling better. Head's a little more clear. Once again, thanks for checking in. We'll wait here a few minutes for people to hop in the stream. Yeah. Thank you for saying that. I know it might seem a little ridiculous to some people, but I'm kind of like I would almost consider myself a crazy cat man. A little bit. So I really do love them. Z asks, "Is it true the vaccines are magnetic?" I'm not sure, and I'm not going to try anything. For those of you who want to see my other cat while we're just waiting, I can kind of pop up the camera there a little bit. I can't really point it out with my mouse, but her paws are hanging off the cat tree there, so she'll be listening to class today. All right, let's see. I messed up my webcam here. All right, that's better. So the cat that passed yesterday, she was 15 years old, which is pretty good for a cat. I've known cats who were older than me who lived to be 22. I've seen 30-year-old cats too. But she was 15. And then Patty is up there on the cat tree. She's about 5 years old. Well, it is 11:20. It doesn't look like there's very many people in the chat, but hopefully we can get a few people to come in here. Now, I did expect you guys to watch the uploaded videos I did yesterday. I will be reviewing them today, so if you didn't, no worries about that. Because I will I still expect you to watch them, because today I'm going to kind of speed run. I'm going to kind of speed run the first part of it, and then we're going to hop right into the kind of hard stuff. So before we get started, does anyone have any kind of questions they want to get out of the way? I do know some of you are having trouble with the cards assignment, so if you need like some more help, I know I've got a few people coming to office hours after class today. But if you guys have any quick questions about it, something that I can probably answer in a 2-minute time frame or so, please throw them in there. Other than that, I'm just going to kind of review our notes from the video, and then we're going to hop into today's examples. Well, we're going to do examples and we're going to finish out our notes. So, to get started, yesterday, this is on Web Campus, and I should have typed these during the recording. The first thing I talked about was the implementation files, where we're creating one object code or one program from multiple files. So we're going to be doing this a lot from here on out. This is very common to do with C++, to have multiple files. I promise it's not very hard to do. You just have to understand how to do it. So if you recall from the discussion of assignment 3, which, by the way, the due date is posted. Now, that assignment is the easiest one you're going to have so far, as long as you understand the inheritance part of it. I mean, the code already runs almost as intended, so it should be the very easiest one, and it's due on Saturday night. So you only really have 3 days to do it, but I suspect some of you, if you're really understanding how this works, could finish it in maybe 15 minutes or less. Okay? So that assignment, you have to do this implementation file thing, where we have the main.cpp, we have the header file, which is for the player class, player.h, and we have the implementation file, player.cpp. Okay, so just the class definitions and function prototypes, or the class, those are in the player.h file. And then any function definition for those classes or those prototypes is in player.cpp. Today, I'll try to do an example of that so you guys can kind of follow along with that. But if you need some more time on that, please review the video. We talked about header guards, or I talked about header guards. So you'll see those in there. But this is just some code you can use to, if you want to include IOStream in every single file that you have. For example, let's say you have 30 implementation files and you don't know where you included IOStream. You can kind of guard the include statements with these guard statements, and it will prevent your compiler from complaining at you. So you will see these in future assignments. Please review the video if you need, and ask me questions if you want to go over that. These here are not on any kind of test question, and these here are not on any kind of test question. These are just kind of basic implementation things that we use in C++. So the first thing I talked about was explicit conversions. Okay, I'm going to kind of review that today, where you can explicitly convert some types of ints or some types of variables into other variables. For example, you can explicitly convert, say, an integer x into a float by including float in front of it. Now, in order to do this, it needs to be needs to be something that's legal. So in general, numbers work. Same with pointers, which is the main discussion of today. If you try to do this, compiler likely will not be happy with that at all, because it doesn't really know what to do. That's kind of when you pull out the toString function if you need it. But the syntax for that is, say you have type 1 and type 2, and you want to assign variable 2 into variable 1, but their types are different. You can try to explicitly convert it up front here by putting that in parentheses. So now let's get started talking about the main subjects from yesterday in class. The first one was these operators. Most importantly, the ampersand and the dereferencing operator. So I'm just going to remind you guys how that looks. I'm going to pull open just a brand new file. And I'm not going to go as in depth as I did in the videos, but I will just quickly run a little bit of code for you. And if you have any questions about it, you can let me know. Hopefully you understand, though, what's going to happen here. For those of you who did watch the video, does anyone know what I called this type of variable? And by this type of variable, it is just one that's kind of declared in main like this. In the sense, you know, it's just the type, and it's its name, and then whatever value is assigned to it. I'm going to give this maybe a 32.1. Codemax says static. That's completely correct. So if you're confused now, I'm sure you might be. These are not static member variables. Recall from previous classes, I talked about things that are static in classes. I call those things static members, meaning you have to listen for the member part. This is just a static variable. Okay, this is just a static variable. And the reason it's static is because of the memory. So let's see here in the notes if I can find it. Here it is. And once again, look, I say not to be confused with a static member variable. In any static variable, the memory is granted before the runtime. So when you compile your code and then you run the program, the very first thing your program does kind of before the runtime is it goes to the operating system. It says, hey, may I please have some memory to store this? May I please have an address to store this value in? Now, throughout the runtime of this program, the memory of X, the address of X will not change at all. And that's why it's considered static. The address will not change during runtime. Okay? So that's the main key of that. So let's say we declare some value like this. Now, for those of you who watched the video yesterday, if I want that address, if I want to see the address that X is located in, what can I type here for that? And let me see if I can get Bobby up and running here. And X, yeah. Code is on top of it. Little tacker's on top of it. Flyer's on top of it. Well done, guys. Thank you. That's exactly what we'll do. That's exactly what we'll do. Tell me, what is the address of this variable? Well, I'm going to apply this address of operator to that X, and it's going to tell me exactly what it was. Can anyone tell me what format an address is in? What's the format of an address? What did I call it? I'm getting kind of out of. It's in hex. It's a hexadecimal number, right? Flyer, close enough, right? Yeah, it's hex. It's a hex value. So don't get confused. This is just a number. This is just a number. But it's hex, okay? So you're going to see A's and B's and C's and D's and E's and F's. So you can get the address of that variable. And no matter what we do to that variable, as soon if I come down here and I assign something else to it, I say X is now equal to 37, the address will not change. Okay? The address is static. Whatever is stored within the address will change, but the address itself is static. So then we talked about the dereferencing operator. Now, the dereference operator doesn't make sense in this context yet until we start using the pointers. But if I wanted to dereference this value, what can I do to it? If I wanted to say, hey, can you please show me the value that's within this address? What can I do to that? Yes, I apply what's called the dereferencing operator. This is the dereferencing operator. It's going to uncover the value stored at that memory address. Okay? So all you have to do is put this little star here up front, and you will see that we're going to dereference this value. We'll figure out what's inside that address, and it's going to work. You see we stored 37 in there, and that's what we got out of it. All right, so this is our deref, right? Deref op, and then this is our address of op. And that's pretty much that. So we're going to talk about more variable or more operators today. We did talk about the size of yesterday, right? We can see what is the size in bytes of a type if we want to. And this matters because I will kind of give you a little formula down below. But before we do that, let's review what pointers are. So a pointer is a variable that holds an address. And why do we care about this? Well, we want to control dynamic memory in C++. Now, a dynamic variable is memory that is granted during runtime. Means while the program's running, the program will go to the operating system and request an address to store something. Now, when this address is granted, we may be able to change the address of some variable, hence the dynamic part of the variable. So that's kind of where we ended off. So I'm going to kind of declare a pointer, and then we're going to get back into this addition thing that I was talking about. So if we want a pointer to hold some address, we're going to declare it like this with the same star, okay? So one of these stars, when it's used on an address as an operator, it will dereference the address. But if we want to declare a pointer for, say, an integer, this holds an integer address. We could declare it like this. And this star here indicates that it's a pointer. And if I want to assign something to it, I can say this is equal to the address of x. What does this say? This says pointer is equal to the address of x, right? And then if I want to see what value is stored within inside that pointer, I can dereference it. So I apply that dereferencing operator out front, and we'll see what is stored inside there. I can also just print out the pointer to see, to see what's in there. I don't know what I'm doing here. And so just to prove to you guys that this is a pointer, it's an address. We'll see the address print first, and then we'll see whatever value is stored there. There's one thing that I want to do. I'm going to get rid of this float here for now. And after I run this code, we're going to do a little puzzle to test your understanding of pointers and addresses. All right, notice here that it's the same address and the same value. So it's puzzle time. I have these all declared up here. Let me do this. I like that. And I like this. So let's say I want to assign something to the address. Say I want to store something in the address. Now I haven't gone over this yet. But does anyone have an idea on what I type? Let's say I wanted to put something inside of the int pointer. Something like this. What else do I have to do to this statement to indicate to the compiler that I would like to store 47 at that address? Like I said, I haven't gone over this yet, but Cherry got it right. Yeah, we have to dereference this. We have to dereference this this value here. So we have to deref the address to store an int. That's exactly right. So let me put that kind of in the notes. As long as a pointer contains an address, we can store values at that address as long as we deref the pointer on the left-hand side of the assignment. So that might look like this. And if I use the same example I did up there, I'll say something like deref the variable name is equal to, say, 47. Something like that. So that'll work. So now puzzle time. What's the values here? So obviously if I dereference this, you can take a guess at what's stored inside that pointer. Now what's stored inside of X? Puzzle time. What will we see here? You think 42. So X is equal to 42, right? And then we say that the int pointer now contains the address of the X. And so then we dereference whatever that address is, and we assign 47 to it. We say put 47 in this address. So some of you said this, maybe someone corrected themselves up there, but you think this will be 42, and you think this one will be 47? Well, let's see. They are both 47. Whoops. Sorry about that. They're both 47. And why is that? Yeah, so question here says, int pointer took the address that X had. It did. They actually, the int pointer and X are the exact same address, right? Yeah, so here we said this pointer contains the address of X. And so X has the address, let's say 0x2, and now the int pointer contains 0x2. So if we go to that location in memory and assign some value into there, it's also going to change the value of X. So this is also 47. In a sense, this is what we might call this. Int pointer and X are aliases. In a sense, so let me kind of define that for you here. An alias is two variables use the same address. So you said, what happens if int pointer equals 47? Well, for one, the compiler would complain. And the reason it would is it would say, these types are different. It says, int pointer, this stores addresses, and you're trying to assign an integer to me. Now, we might be able to literally make this, I'm not sure if that'll work. Probably not. Maybe I can convert it. I can, yeah, let's try that. Okay, so that works. Yeah, I guess I could convert this integer into an integer pointer and then assign it. But yes, you're completely right. That's exactly what's going on here. This does not work because this is a pointer and this is an integer. So if you want to store something inside of it, you have to do this. So hopefully that's making sense. I'm going to rename this one. This is going to be alias. And I'm about to move on to the next part here, okay? So if you guys have any questions about dereferencing and address of, let me know so we can come back to it. The next thing we're going to talk about now is basically arrays and how they work in C++. How all arrays work in C++. So let me grab my favorite stuff here. I want that. And so recall, I'm going to do this Excel thing that I did the other day. I did upload this, by the way. So you should have access to it. Maybe I didn't upload it. So I'll upload the new one that we do. So I'm going to zoom in here. I want to get rid of this thing. Go away, please. I guess Excel is taking its sweet time to go away. All right, so here we are. So imagine this is a strip of memory. Let me make sure that you guys can see and I don't go off the screen here. So let's imagine that this here is a strip of memory. Okay, so you can see it here. Maybe I'll give it a nice kind of dull color. That is a strip of memory inside of RAM. Kind of want to see the chat here too. And so each of these cells, this is what we'll call them, cells, they have a location, right? And each of these cells contain 1 byte. 1 byte of memory. Now, 1 byte is 8 bits, right? 1 byte is equal to 8 bits. So that might look like 1011, 0111, something like that. I'll kind of put the space in between there. So each of these contain 8 bits. And they all have their own address. So we could say that this is 0x00, this is 0x01, 0x02, 0x03, so on and so forth, right? I'm going to kind of center these. I'm going to bold them and I'm going to make them just a little tinier. Not larger, but like that. Yeah. So each of these have their own address. And so whenever we apply size of to some variable, let's say int x is equal once again to 47. And if I say see out the size of this variable x, we will see that this is a size of 4 bytes. So whenever we declare an integer in our program, it goes to the memory and it says, I need these 4 bytes for my integer. 1, 2, 3, 4. And so let's say that int x is stored here. And let's say it equals 47. Now, if I applied and of x, can anyone tell me what would pop out? By referencing this example, if I applied the address of to x, what would I see on the screen? Yeah, you would see an address, but specifically which address? I kind of gave them to you, right? Specifically, which address do I see? Yes, exactly, Cherry. We would see this one. We would see 0x00. This is where x exists. And so 47, I think, looks like this. Definitely there. 3, 4, 5, 6, 7, 8. And then this one will be, I have to think about it. I think we'll have a 1. Well, I'm not going to, I can do it for you, okay? I'm a computer scientist. I know how to convert it, but I'm not going to. 47 in binary. because we have to, you know, we have to kind of move along here. All right, so it looks like it's 6 characters long. So this is going to be 0010, sorry, 0010, 1111, which will be, for those of you who don't know, 1 plus 2, which is 3, plus 4, which is 7, plus 8, which is 15, plus 16, which is nothing, plus 32. I think 15 plus 32 is 47. Yes. So that's how we did it. So we're there, right? So 47 is stored within this address. And when we apply this, we're going to see 0x00. And so we can actually do addition on our addresses, okay? So I've gone over this already, but I'm just going to do it for you. If I add integer numbers, this is called pointer arithmetic, to the addresses, you are going to see, let's just say 0, let's say nothing. You're going to see something very distinct happen. And I want you guys to tell me why it's doing that, and then we're going to talk about arrays. This is not what I wanted. That work? All right. So this is the address of X. And then I add plus 1. And so what does this go? This goes C. That's C. So C plus 4 will be D, E, F, 0. So how far did I move, and why did I move that far? And then I took what? This address plus what? 1, 2, 3, 4. Why did I add 4? Why is it adding 4 every single time? I did talk about it. And there's a hint here. There are 4 bytes. Now, specifically, what is 4 bytes? The size of an int, right? Exactly. Ints are 4 bytes exactly. And so if I add, this means I want to add the size of an int to this address. Ints have exactly 4 bytes, right? So if I made this a double, for those of you who watched the video, how many am I going to add each time? Take a guess. Some of you will know, right, if you watched the video and didn't fall asleep. 8, right? The size of a double is 8. So you're about to see where we're getting with this. And you guys are about to open a whole new world of understanding. Doubles are 8 bytes. So 8 plus 8 is 9, 10, or 9, A, B, C, D, E, F, 0, right? 8 bytes. So pretty much, if I said and X plus 1 here, we're going to go all the way to this one. We're going to go straight to this. I'll make it red. We're going to go straight to this cell. If I add 2, we're going to go straight to this cell. Right, I did the Hello World example yesterday, right? So now it's time for the crazy thing. First, I want to give you the formula. So let's say we take some address plus, I don't know, let's say int x. Int x equals, you know, some value. And so if we take address plus x, that is equivalent to the address plus x times the size of int. Does that make sense? That's our formula. You take whatever the address was, and then you're going to take x, whatever that integer is, times the size of an int. So in this case, if x is 2, we're going to take 2 times 4, which is 8, and we're going to add 8 to this address. So now, begin arrays. Now we're going to go back to this hello world thing that Ali talked about. Let's pretend that this is a character. Characters are, can anyone tell me how many bytes? That's fine. 1, right? They're exactly 1. They're exactly 1 byte. Super easy. They're exactly 1 byte. So in each of these, we're going to have something. As Ali mentioned, we did hello world, right? You guys have probably seen this way too much in your life. And if you continue on doing this stuff, meaning if you continue doing computer science, you will see it even more. So try to bear with me. But we're going to store H in this byte, E in this byte, L in this byte, L in this byte, so on and so forth. So let's do that. I kind of did this one yesterday already, so I'm going to do something else here. So I'm going to take a character array. This is my string. And it's what's going to be the size of it? Well, let's do hello, which is 5, and then world, which is 5, maybe plus 2. So maybe say it's 12. And that's equal to this. I'm going to make it vertical here. Please excuse my formatting, but 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And let's kind of go backwards here. World. Space O L L E H. All right, understand? Now it's like a string, right? But it's a character array. This is a character array. So prepare to have your mind blown, okay? Everything you knew is about to make sense. Everything you thought you knew is about to make even more sense. The size of this array is going to be int, maybe 12. And so let's, thank you. Yep, thank you. So, tell me, you guys have never seen this before, but does anyone know what prints when I do this? Can anyone take a guess? You may have never done this before, so I won't blame you, but what does this print? Does anyone have any ideas? Notice I am not indexing it. You say hello world. Are there any other guesses? Megitsu says nothing. I'd say that's maybe a little closer. Well, let's take a look. Coda says address. I think he's right. Or I think they are right. Looks like we got nothing. Oh, whoa. Okay, I'm a little upset. I'm a little upset because the compiler assumed what I wanted. So, you know what, little attacker, you win the gold. Coda, you also win the gold. Surprise! This contains an address. This my string does. And I will, let me see this. Let me just make sure I don't confuse you more. Yeah, accidental win. Oh, man. Nice job. I'm mad at the compiler. I really am. Okay. So this is an address, okay? I swear on my life that this is an address. Now the compiler was like, this is a character array, so I know what you want. Okay, but no, that's not what I wanted at all. My string is an address. So look, do you see me how I dereference this? Now some of you were paying attention, so you should be able to answer this, right? But if I dereference this, what prints? My string is basically an address for chars. It's an address for characters. Maybe if I did this, it will make our life easier. Let's say I make a character pointer. My char array, and I say is equal to my string. It will work. Should work. All right, there we go. Yeah, so I confused you. I'm sure I did. But let's do it this way instead. So we have our pointer here. And I say, hey, please look at this address. So if I print this, we're going to see an address, as I said before. Right, so Cherry asked a very good question, and we're going to answer that next. Oh, man, I'm so mad at this compiler right now. Look, do you see this, though? I'm so mad at this compiler right now. Sorry, folks. Let me fix this. Stop doing that. You think you know what I want, but I don't want that. I want that. Thank you. I'm not sure what happened, Z. So guys, don't get mad at me. I made this int. Okay, so I'm gonna explain to you why the code is doing this. Strings have been around for years. Yeah, Sally would never. You guys make me laugh. Strings have been around forever, okay, since like 1960 something. And they were always handled as character arrays. And so C++ has done something here where they think that whenever I make a character array and I print it out, I want to see like the whole string. But notice when I make this an int, array, it works the way I want to. It says, oh, this isn't a string, I'll print the address. So notice here that it prints the address. So as long as you understand that, we'll go back to using characters because I think that's the best way to do this. And if you don't understand what I said, please let me know. So I dereference this, right? And what does it print? It prints H. Now I'll tell you why it does that. Prints H. Why does it do that? Well, I said, hey, this is a pointer for a character array. So how big is a character? Well, it's 1 byte, right? A character is 1 byte. And so basically what I say is, hey, please go to this location and dereference this. Dereference this location and tell me what's in there. What is in there? H. H is in there. Now, I don't remember what I said yesterday. I think it's like 47, right? I think that's what I said. So it's 0, 1, 1, 1. I think that's what an H looks like. Or at least I'm close. So I'm going to take a guess. Take a guess, everybody. Let's say I add 1. Let's say I add 1 to this address and I dereference it. What do I see? E. That's yes. We see E. And why does it do that? Well, let's say we're going to take this address 0x00 and we're going to add 1 times the size of a character. The size of a character is 1, so 1 times 1 is 1. So take this address plus 1 and we're at 0x01. Dereference this address, please. We get E. All right. So guess what? What do I get when I do this? Well, I'll use my string instead. What do I get when I do this? E. So you know what this means? It means that this is equal to dereferencing the address plus I. They are identical. Is your mind blown yet? You've been using this thing forever. This bracket thing. You've been using this since CS135. What are you doing? You're taking the address, you're adding some number to it, and you're dereferencing it. They are exactly the same. It's 100% identical. That's how arrays work. Does that make sense? Does it make sense? Look, if we add 2 and 2, we're going to see L. You can feel your brain expanding. I hope so. You've been using that forever. That's what it does. So that is an operator that we're going to add to our notes. L, L. It's the same thing. So let's go to our notes. Let's go find our operators. So if you use 0, you could dereference a pointer that is not an array. Yes. Yeah. Let's play with it, actually. Let's play with it a little bit. I'm going to make another thing here. And I am going to copy this a little bit just because I hate typing. So we're going to talk about the bracket operator. This is dereference. This is a dereference operator. Brackets are a dereference operator. Add memory address plus I. It is a unary operator. We're going to pretend that this is a pointer. And if we see out X located at 3, it's exactly the same. This is a test question, okay? This is a test question. I'm going to say, can you please print the 4th index in this array in 2 different ways? This is a test question. They're exactly the same. So we're going to play with it. And this is where C++ gets dangerous. So the first thing is Terry asked this, right? So let me make some int pointer. I'm going to make, say, an int x here equals 47, as I've always been doing. And then we'll make an int pointer is equal to the address of x. And then I will see out dereference I pointer. And I will also dereference I pointer, which will be this, IPTR located at 0. And then I will also do the exact conversion that we did here, I pointer plus 0. This should compile and this should work completely. Of course, maybe the compiler is going to disagree with me today, or the runtime, or the computer, or whatever it is. They're going to say, you know what? Your class, I'm not going to comply today. 47, 47, 47. So you're right, Cherry. You could use bracket 0 to dereference a pointer. Now check this out. Do you think this is going to work? Do you think that's going to work? And if so, do you have any idea? So you say segfault. Perhaps. Ali says no. Well, let's see. Let's see what Bobby thinks today. What is that? I mean, don't tell me what the number is. Does anyone know what's happening? Right. Cherry says garbage value. And Magum says, are those the next places? Yes. So imagine it like this. Here we have int x, right? It's equal to 47. And it said that these cells are for the int. And so I have this address here. And then, so since I have a starting address, I can add whatever I want to it. I said +3, so I'm going to go, let's see, +1 are these ones. Let me scroll over here. +2 are these ones. And then +3 are these ones. So whatever garbage value is hanging out over here is what we're looking at. There's just something hanging out over here. This memory might be being used, maybe. Oh, English, come to me, please. It may being used. You know what I'm trying to say? It might be being used. It might be being used by another program. This memory may not be being used by another program. It's just sitting out there, and we went to it. We found it in our program, and we said, please tell me what this representation, or please tell me what this says in int language, please. What is this string in int language? Thanks, I'm trying my best. What is this in int language, please? They say, well, from my interpretation, this is 560,229,490. Does that make sense? So we're going off into no man's land here. So at this point, we should understand what a pointer is. We should understand how pointer arithmetic is used. Okay, what are the only operations? This is a test question. What are the only operations that we can use on a pointer? I talked about this. We can add and subtract, okay? It's arithmetic. It's not, well, I would say that. We can't use multiplication or division on addresses. But we can add and subtract integers from addresses. Let me add this up here where it belongs. So stop me and tell me if I need to go back on anything that we talked about. But remember, we've gone over these addresses. We've talked about what they do. And now we're about to get into the scariest part of pointers. It's about to be Halloween up in here. And we're going to talk about dynamic variables. Yes, only addition and subtraction. Dynamic. Time for dynamic stuff. All right, let me grab my stuff. So, first we're going to learn how segfaults work. Have you guys programs ever segfaulted? I'm going to guess yes. Today we're going to learn how they work. Segfaults. Let's start with segfaults. So let's say I have a pointer, and I do this. Now this is a legal thing, so let's talk about that before we talk about segfaults. Yes, exactly. Yeah, you're right. You're completely right. So why do we experience segfaults? Well, to begin, null and null pointer is an equivalent to kind of 0. Kind of equivalent to 0. And when we talk about null, and for the rest of your life, especially if you become a database administrator, you're going to deal a lot with nulls. And this means empty. It means whatever this is empty. There's nothing here. Now, null and null pointer are very handy values because recall from assignment 1, you saw those NA values that were in that CSV, right? And it says this int, this age might be equal to NA. And I said, if that's the case, please store -1 inside of that integer there. Now we're using -1. What if we were storing an integer variable and all valid integers, like every integer is a valid value for that variable. So we say int x, this thing can hold anything from -infinity to infinity, as long as it's an integer. And then I say, also, it can be this value NA. So if you store -1 there, because it's NA, how do you know that it's an NA value? You know what I mean? It's kind of confusing in the sense that it might be -1 or it might be NA. So null and null pointer come in handy because they tell us if something is empty. And for assignment 1, I would have much preferred for int, weight, and height, those values cannot be negative by definition. So the -1 was okay, but I would have much rather had them be null or null pointer because that makes more sense. So hopefully you kind of understand what a null is. And so what does this say? This says this is an empty address. So take a guess. What happens when I do this? I'll tell you what happens here. This will either print, it'll either print 0 or nothing. But what happens if I dereference it? This is a pointer, right? This is a pointer. So I'm allowed to dereference it. I'm allowed to uncover whatever value is stored at this address. Now I've given you a hint. What are we talking about right now? Someone tell me what happens when I run this program. I believe in you. Seg fault. Yes. Let's do it. I swear, if it printed hello world, I would end the stream. I would end the stream. I would be so mad. Oh, that would be the worst day of my life. Okay, so seg fault. It seg faulted. Why did it seg fault? Well, we dereferenced a null pointer. We dereferenced a null pointer. So sometimes the main thing happens when you seg fault is you go out of bounds on an array. That's usually what happens. So if you go negatively out of bounds, likely you'll get the seg fault. And sometimes you'll just kind of go past the bounds of memory or something, and you'll try to dereference that address, and you'll get a seg fault. So what happens when you seg fault? Well, you dereferenced a not valid address. Yeah, so Arceus asks, we cannot dereference null and null pointer. That's exactly correct. Magum asks, are there any words for dereference that help with understanding the action? Tell me how you think about this. Maybe we can come up with a better one. I like to say uncover whatever is stored at that address. So I'm going to go to that location and I'm going to try to open the box. I'm going to try to uncover what is in the box, what's in the memory address. Tell me if that's good. I have to blow my nose real quick. Yeah, so you're happy with that? Kind of uncover, go to wherever it is and uncover it. That's what I'd call a dereference. Locate. Locate is the address part of it. The uncovering part of it is the dereference. So I guess the find action is what is the address. The open box, the uncover action is dereference. So I asked the question, what if I would like some memory during runtime? Well, let's talk about some operators. We're talking about 4 more operators. It's really just 2. It's really just 2 operators, but they can be used in kind of 2 different ways each. So the first one we're going to talk about is new, and then we're going to talk about delete, and then we're going to talk about new that, and then we're going to talk about delete that. So new, this operator requests memory from the operating system. These are kind of functions too, I'd say. We're going to call them operators, but. So new returns an address. Okay. So what's the syntax of that? Well, first, you must use a pointer for this. And so if we're talking about the syntax of new, we're going to say, hey, int I pointer is equal to, say, maybe null pointer. And then we're going to say, hey, I want my I pointer to contain a new int. So let's give the general syntax. Whatever the type is of your pointer is whatever type you're going to use here. So let's talk about this. Let's say, hey, I'm going to say, hey, I pointer, please have a new int. So this requests memory from the operating system, OS. So if I do this up here, I guess I'll just uncomment it. I'm going to see nothing, okay, because the pointer is equal to 0. But then if I do this afterwards, I'm going to see something. And then don't worry about this part yet. I mean, we will talk about it very shortly. But let's just run the code. So what did iPointer contain to begin with? Well, it contained a null pointer, right? So as soon as we print it out, we're going to see either 0 or nothing. You can see here we see the 0. That is a null address. That's a null pointer. And so then I went to the operating system. I said, please give this an address. Please give this an address. And so then I print it out, and guess what? Now, iPointer contains an address. And once it contains that address, we can say, hey, I would like to put 3 here. And then I can see out 3. So hopefully you have a general understanding of what new does. New says, give me some new memory, please. Now this is, by definition, a dynamic variable. This is, by definition, a dynamic variable. So if we come back up here, a dynamic variable is any variable in which the memory is granted during the runtime. So in a sense, creates a location. Now this, what does delete do? Well, let me see my notes here. Delete address returns the address to what we'll call free memory. So tell me if this doesn't make sense, but the operating system, the reason every computer has an operating system is because it's always managing the memory. So the computer I'm working with now has, I think, 32 gigabytes of RAM. And so there's 32 gigs of memory kind of available. And your programs use the memory. And so all of the programs have to go to the operating system and they say, hey, Overlord operating system, can you please grant me some memory? I would like 2 gigabytes, please. Say I pull up my Minecraft server, you know, and I say, hey, please give me 2 gigabytes of memory for me and my friends and I. And the operating system says, yes, okay, here's your 2 gigabytes worth of memory. So the same thing I'm doing here is when I call new, I'm going to the operating system and I say, hey, I need 4 bytes of memory. And the operating system says, okay. Now, the important distinction is that the operating system is not going to give you memory that's already being used. So if I'm using 31 out of 32 gigabytes of my memory, and I start up my Minecraft server that wants 2 gigabytes of memory, Minecraft is going to go to the operating system and says, please give me 2 gigabytes of memory. And at that point, you'll see something like bad Alec. I know that some of you have seen that error already, in which the operating system says, well, I have no free memory to give you. I don't have that much free memory. I can't do it. So, what does delete do? Can anyone tell me, based off of that small example that I gave, what is the idea behind delete? I may have even typed it out in the notes already. I already forgot. But what do you think delete does? I'll give you a few Jeopardy moments here. See how we're doing. Looks like we're doing okay. Connection's good. All right. So I'm going to tell you now. So if anyone types it out at this point. All right, we got one here. Little Tacker says, allows the variable's memory to be reallocated. I like that. I like that well enough. I would say more distinctly, this returns the address back to free memory. Yes, yes. So Cherry nails that. Now, Migisto says something very important distinction here. He says sets it back to null. Well, not quite. What delete does is it says, hey, I'm no longer going to use this memory. Operating system, you can have it back. You can have it back. So I don't want it anymore. So it says, OS, I am not using this memory anymore. You are free to give it to someone else. Cherry asks, what does null mean exactly? Null means empty. Null says there's nothing in here. Now, maybe I can better explain to you why we use this in just a moment. I'm going to answer Z's question, and then I'm going to show you the reason we have this. I'm going to show you the exact reason we have this. But Z asks, if it deletes the memory, what value will be 0 or garbage value? Well, let's see. I'm going to print after returning address. After returning address, this is our value. All right, so what did I do? I requested memory from the operating system. I then print out whatever that address is. I then assign something to it. And then I print out whatever that is. It's going to be 3. And then I say, hey, operating system, I don't want it anymore. Have it back. And then I'm going to print out what the value of iPointer is, as well as can we dereference it. Whoops. What am I doing? So notice that, I don't know if I can highlight both of these. Notice that after I return the address to memory, iPointer still contains it. Okay? iPointer is still containing the exact same address. Look, I deleted it. I said, operating system, you can have it back. But then I still know what that address was, and I dereference it this time. Now it's 0. So what happened? Well, I said, operating system, you can have this address back. But then basically I said, I'm going to just keep it, you know, because I want to watch what it does. And so the operating system returns it. And then perhaps some unsuspecting CS135 student is running their code at the exact same time that I'm running this program. And then when they run their code, int x is allocated for them, and the operating system says, hey, this address is free. You can have it back. You can have, or not back, but you can have this address. And so then that CS135 student sets it to 0. But guess what? I still have the address. I still have the address. So now I can do this. Guess what? This will work. And you know what it does? It's going to change the value of that CS135 student's program while it's running. I am directly accessing memory that is not for my program. Do you understand how this is dangerous? Or do you understand what I'm communicating? I'm saying that I still have the same address, even though I told the operating system that it's free, and I can do things to it. And so I think maybe, well, it was one of the students, the output to me looked wild. And I was like, maybe someone from CS302 is accessing your memory. You could do this. You could do this. Does anyone have a good solution to this? How can I prevent something like this? I mean, besides typing this out, what else could I do after deleting the pointer to ensure... Yes, that's exactly what I meant, Coda. I was like, is someone accessing your memory? Someone might be. It's possible. But take a guess, guys. After I delete this, what can I do to the I pointer? What can I do to the I pointer to ensure that no matter what code I type underneath it, I can't mess with that pointer? And there's a term for this. Let me do terms while I'm waiting. Dangerous pointer stuff. So for 1, we have a dangling pointer. For 2, we have a memory leak. And 3, we have a... what do we have? We have an alias. I already kind of mentioned what an alias was. So no guesses, but I'll give it to you. I say, hey, goodbye address. I say goodbye to the address. I overwrite it. Overwrite old address with null. Now, I think you should do this every single time you call delete. It would be nice if delete already did that for us, but it doesn't. So now, guess what happens? I'm going to segfault down here. But at least I'm not accessing that poor CS135 student's precious memory. I'm saying after I return it to the operating system, I'm going to ensure that I don't use it anymore. I say this is empty. This is an empty address. I don't want it anymore. So a dangling pointer is an address that is deleted, right? That means returned to the OS, but not set. A pointer that contains an address. A pointer that contains an address that is deleted, but not set to null pointer. Meaning, we have access to memory that doesn't belong to us. Now, let's talk about the memory leak and the alias. So, guess what? Let's say I don't delete the I pointer. Or let's say I even overwrite it with something else. And then the program exits. Notice I don't have the delete statement. Okay, I called new. And I didn't call delete on it before I overwrote it, or I just exited the program without deleting it. Now guess what happens to the address? The operating system still thinks that that address belongs to this program. So essentially, you grabbed an address and you didn't send it back. You grabbed an address and then you closed your program. And then that address, as far as the operating system knows, belongs to your program. But the program's not running anymore. So what have you done? You've lost an address. You've lost a bit of your RAM. It's gone. It's vanished. Goodbye, memory. I don't need you anymore. Because the most important thing to consider with this is that when you have an address, you know, like you have direct access to it. There are millions, if not billions, of addresses in computers. And so the operating system has to always keep track of which addresses are free or not. The moment that you overwrite this or your program ends and you lose the location to that address, you cannot return it to the memory. It's gone. So I'm going to show you a fun little program. We're going to use it. We're not going to spend time learning how to use it today, but I'm going to show you something that I'm going to mark you for on your homeworks in the future. We have this program called Valgrind. And when I run it using the program, it will check to see if there's something called a memory leak. A memory leak is an address that is not returned to the OS. So there's a lot of text here, and it's kind of large, so I'm sorry. But here's the output of the program right here. This is me running this program. This is the operating system's address. This is the address that the OS said I could have. And then I returned. Notice here it says invalid read. That happened because of this. Probably because of this, actually. But notice here at the bottom, well, here's the seg fault. The seg fault happened. Why did the seg fault happen? The seg fault happened because I dereferenced the null pointer here. But if you come down to the bottom, notice what it says. Leak summary, definitely lost 4 bytes. Why does it say 4 bytes? Does anyone know why it's 4 bytes exactly? And while I wait for that, Arceus asks, so it like slips out of the program. Well, kinda, maybe. It's just that the program didn't return the memory. The program asked for memory and got it, and then it never gave it back. And that can happen in a number of ways. Cherry and Little Tacker say the size of an int, right? That's exactly right. Notice I allocated an int here. How many bytes is that? 4 bytes. I never returned that memory to the OS, and so guess what? I lost an integer's worth of memory. So basically, it just says, this address that was given to the program was never returned. So the operating system doesn't know if it's done with that memory. And so it's kind of permanently just lost. So how does this happen? Overwriting an address or exiting the program without calling delete. So if you overwrite an address before calling delete, address is gone. I don't know what it is anymore. I can't return it. If you exit the program before calling delete, address is gone. I can't return it. So every time I run your programs, when we start using dynamic memory, I am going to run valgrind. And if you have memory leaks, I'm going to tell you that you need to fix them. Please return your addresses to memory. So I'll give you just a small little warning. Computers have come a long way. And so in Java and, your operating system and all sorts of other computer memory systems out there use a thing called garbage collection. And they're going to go through the memory kind of sporadically. And they're going to check each address. And eventually they'll find an address that was being used by this program, but the program is no longer running. So the operating system knows that that address belonged to the program. It also knows that the program is no longer running. And so the operating system will say, hey, I'm going to return this address back to memory. Now, that's kind of a long process. Like I said, your computer contains millions and millions of addresses. So whenever this thing called garbage collection runs, you can't necessarily control it. And so if you are doing development on your own machine and you do an infinite loop calling new, creating memory leaks, I'm not sure what's going to happen to your computer. Okay? So I'm saying if you're doing local development, if you're using Visual Studio Code is probably safe. But if you're on a Mac, and you're running it in the terminal, and when I say this, you're not SSH'd to Bobby, you're actually developing on your own machine, and you start calling new, you may mess up your computer a little bit. You won't mess it up permanently, but I'm just letting you know that you're directly accessing your memory by doing this. So if you're paranoid like me, please use Bobby. Just go to Bobby. Bobby is a tank. And you can mess with Bobby's memory as much as you want. You can mess with Sally's memory as much as you want. So if you're paranoid like I am, do that. Go use the servers. So hopefully my rambling made some sense there. I hope you're kind of grasping this idea of requesting addresses from the memory during the runtime. In that you need to return it. You need to say, hey, OS, please have this address back. I don't want it anymore. So now I'm going to move on. Tomorrow we're going to spend more time, since we're kind of running out of class time. Tomorrow we'll spend more time on the thing I'm about to mention. But we're going to talk about a few things. We talked about new. And we talked about delete. But now we're going to talk about new bracket and delete bracket. So this it does the exact same thing as new, but it allocates an array from memory. So if I called int array, this is a pointer. I say you are equal to a new int 32. This allocates 32 times the size of an int from the memory. What is that? That is 32 times 4, which is a 128, is it? 128 bytes from memory. So new will just allocate one of them. New says, I'll give you one. You can have 4 bytes if it's an int. If it's an int, you can have 4 bytes. If you use new bracket, it's going to say, oh, you want an array. You want an array. All right, I will give you 32 times 4, 128 bytes of memory. So what does delete do? I mean, I'm sure you can take a guess, right? Same as delete, except ensures that the whole block, the array, is deleted. So if we use this same example here, if I wanted to delete this, I would have to say, this will not work. This will only return the first 4 bytes of that memory. So if I want to ensure that the whole array gets returned, I have to do it like this. Okay. So I'm not going to do an example of that yet. Just know that that's what we're talking about tomorrow. We're probably going to do some class stuff tomorrow. I know some of us are still having a hard time with understanding classes. The main thing we're going to do with this is we're going to make our own string class, or we're going to make our own vector class. Up until this point in time, we have not been able to make resizable arrays. We've been using vectors for that. Now that we slightly understand how to access dynamic memory, we can make resizable arrays. So we're going to make our own string class. We're going to make our own vector class. And you're going to kind of understand not only how this pointer stuff works, but you're going to understand also hopefully how those classes work. When will it be the case where I have to ask the OS to give me memory while I'm programming? So I kind of just mentioned it, but that's when the resizable array thing comes. Pretend you have a CSV file from assignment 1. Let's see here. Pretend you have a CSV file from assignment 1. And every day, this CSV file shows up somewhere. Here it is. So today, this CSV file happens to be 5,835 rows. 5,835 rows. So what are you going to do? Open this every day, go into your program and type in new. You're going to type in this array is 5,835 long. Then the next day, you get the next CSV file. This time it's 271,000 rows long. So what are you going to do? Open up your program. You're going to change that value to 271,000 in the array, and then you're going to recompile it, and then you're going to run it with the new CSV file. So the point I'm making is, what if you have a file that you don't know how big it's going to be? You need a way to control how to store it during the runtime. A lot of you guys did this in CS135, and I even saw it in some of your programs from assignment 1. What did I see? I said, please give me the very last element in this array. And what did you type in? Here's what you typed. You said, I would like, if this is our array, I would like it to be 5,335. If the CSV file is going to be different the next day, this doesn't work. Right? What did you have to do? You had to say, well, array.size -1. And so whenever you're dealing with something that you don't know how large it's going to be, you need dynamic memory. It's required. Yeah, I'm sorry. I'm not trying to make fun of anybody. I used to do that, okay? I used to do that all the time. I was a CS135 student at some point too. But this is something that we call that's not general. This only works for one case, one single case. This is not a general solution. This is a very specific solution. So dynamic memory is going to help us for things that need to be resizable. How big is this CSV? I don't know. How about we build the program to work with a CSV that could be any size? And as we read in more rows, we're going to go to the memory, we're going to go to the operating system, and we're going to say, hey, I just found a new row. Can you please give me this memory? Operating system will say, okay. And then you'll say, hey, I just found a new row. Please give me some memory. So, Cherry, I hope that answers your question about why we need this. Now, if you go to a different programming language like C# or Java or Python, they do this for you. All right, it's automatic. And so you might hate C++ a little bit for this nice confusing thing with pointers, but C++ is a very good programming language for operating system type programs. C++ has a large industry, and the reason that it doesn't do this stuff automatically is because some people are so smart at systems programming that they know exactly what they want, and they don't want it done automatically. And so in C++, whenever we want a dynamic variable, we're going to use these very low-level operations. And if we want to make it automatic, we're going to make a class. Vectors do it automatically, right? Do you guys remember this? Say I make a vector int myArray. Of the operators we learned about today, does anyone have a guess about what happens in this function? Specifically pushback. So of everything we've talked about today, does anyone have a guess about what happens in that function? You could be very simple with your response. You don't have to give me a paragraph. I'm just wondering if you kind of understand what happens in this function. Of course, it adds something to the array, right? But does it do anything related to what we talked about today? We're running out of time here, so I'll only give you a few moments for that. All right, I'm sorry if you're typing it out right now. This function calls new. Do you understand? Pushback is adding something to the array. It's making it resizable in a sense. This function is calling new. This function says, hey, I need one more spot for my 5. Please give me one more spot. Now vectors have a destructor. All right, talking about the classes again, vectors have a destructor. You know what's called in the destructor? Delete. So I understand if you're confused. Never fear, we're going to go over it tomorrow. But this new and delete thing, we've been using it. We've been using it, and we're going to use it more. So that's all I got for you today. I know I've got at least 2 people coming to office hours, so if I'm not in the call, that means I'm probably helping someone else. Please just send me a message, and I'll do my best to go back and forth. Ask me questions. You know, the cards assignment is due tomorrow, so please get working on that if you have not already. Assignment 3, I made the due date for that. I already talked about that. And that's all I got for you. So thank you for coming to class today. I hope you're not too scared yet. about pointers. I hope you kind of understand how addresses work and how arrays work, right? We talked about this thing. I hope you have a wonderful Wednesday. I hope you don't burn in the inferno. And yeah, thank you. Hope you guys have a great day. Goodbye. You're welcome. You're welcome. Ali says, when will the grades be A1? Ugh, English. When are assignment 1 grades posted? I was hoping yesterday, so I'll have to check in with Christine to see how she's doing. But it should be coming up like very soon. And yes, Christine or Ali, you'll see it under grades on Web Campus. With a little comment too. So I'll get on that. You are welcome. You are welcome. You are welcome. You are welcome. And you are welcome. And you are welcome. All right. I'll see you guys tomorrow. Thank you.